leading one. Z is very sad. So what's the consolation price for Z? Minus this plus this, minus this plus this. Oh, sorry, minus this plus this. Sorry, I did a weird operation. As I said, please practice row reduction, because if you are like me and you don't practice it except in the session, you end up making silly mistakes. This is an example of the silliness of my mistake. Right, and also, speaking of mistakes, I am human. I mean, if I were, a robot, I'd have more hair or something. I'd have more muscles. Anyway, I am human. I make mistakes. So sometimes, let's say Evan didn't catch this and this stayed the -1, and then you're looking at the work later and you realize that, it should have been 3. I mean, please don't let it shake. Thank you. Please don't let it shake your understanding of mathematics, right? Like, just don't let it ruin your mathematical education. Like, sometimes I make silly mistakes, and they are silly mistakes, and that's it. I don't know if I told you this, but once I was teaching at McGill, of all places, and I was doing a continuity question, and I did I can't remember the exact question, but it was a continuity question, and I did 6 + 1 is 6. In my brain, I was thinking of something else, and I just did times. It flipped. People just flipped over this. Even one person emailed me saying, in what case does 6 + 1 = 6? When can we use this? And I felt bad for the level of stress that person must have been under, right? Right, just please do not let my small mistakes shake your understanding of mathematics. Andrew, I was mean. I wasn't mean to the person. I told the person, look, it's a mistake. It's don't worry about it. Just don't be stressed. Try to relax. Try to sleep. No, it just created all sorts of just emails. Anyway, so stress happens. We are all under stress. If you find one of those, just please laugh at it. If you want to tell me. But you are good at this. Just believe that you are good. Then you caught a silliness that I did. Anyway, back to this. So as we were saying, X got its leading one, Y got its leading one, Z did not get a leading one, so Z is sad. Consolation prize for Z, Z gets a parameter. So this is what we call a parameter. This is a fancy way of saying Z can be anything. A parameter, that means Z can be anything it wants. As we talked about it earlier, Z is a free variable. And now we're going to solve in terms of Z. So for example, the first line tells me directly that X is equal to 3. So that line does not involve any parameters. This line, on the other hand, says that Y plus 2Z equals to -2. So when you move the 2Z over, you will get Y is equal to -2 minus 2Z, and Z is equal to T. So -2 minus 2T. Right? Sometimes, so that's our solution for any T. That's why we say we have infinitely many solutions. Sometimes they ask you to write it in vector form. So you write it like this: a vector X, Y, Z is equal to a vector of constants plus T times the coefficients of T. So X is 3 and there's no T in there. Y is -2 minus 2T, and Z is 0 plus 1T. See here, they said, write out a set of solutions. So for this problem, I guess it would have been this or this. Either way is fine. Okay, I want to show you one from 2019, where they went all crazy and gave all sorts of parameters. Nope, here we go. Hey everyone, here we are. So this one is from as practice to all the concepts that we just learned. Let's talk about this problem from 2021. Right? Somebody asked me if I'm posting the by topics, like the midterms by topics. I wasn't planning on posting it because you have it from your teacher. but if you think it would help you, I mean, I could just place it after this document, but you have all of these midterms. I didn't change the midterms, right? I just like broke it down by topic rather than by year. If you feel it helps, I could add it to the end of this, but they're literally the same question. Then I will do it, Matt, no problem. So how about I give you 30 seconds to solve this? Let's agree on names for our variables: x1, x2, x3, x4, x5, and x6. Ah, see, they already told us this. So go ahead. So x1 got its leading one, x2 got its leading one, x3 is sad, it doesn't have a leading one, x4 got its leading one, x5 did not get a leading one, and x6 got a leading one. So we have two free variables, right? We have two free variables. So x3 gets the first parameter, so let's say x3 is t, x5 gets the second parameter, so x5 is s. And now we read each one of these lines and we write down things in terms of, like, we write down the solution. So for example here, this line tells me that x6 is equal to 9, right? This just says x6 equals to 9. There's no parameter in there. Now what is x4? This line. When you move this to the other side, x4 is 2 minus 3x5, and x5 is s, right? So this says that x4 plus 3x5 is 2, and then you move the x5 to the other side. So x4 is 2 minus 3s. Okay, so let's see. This one, x2, you're going to move the 6 over and you're going to move the 5 over. So that's 7 minus 6x3, and x3 is t, minus 5x5, so minus 5s. And x1 is equal to minus 1 minus 4x3 minus 2x5, so minus 2x. Now they want it in vector form, so we're gonna write it in vectors. So this is x1, x2, x3, x4, x5, and x6. There's a vector for constants. There's a vector for t's. And there's a vector for s's. So x1 is minus 1, minus 4t, minus 2s. 7, minus 6t, minus 5s. 0, 1t, no s. 2, no t, minus 3s. 0t, 0t, 1s, and then x6 is just 9. And that is what it is. Do we get this? Are there any questions about this? Any comments? Any concerns? I'd like to do one more very, very quickly. The 2021 one for reason. Just, solve this. There's a small reason why I'm doing this. I'm just being extra careful. It'll take us 2 minutes, and then we can go to linear transformations and basically just go from there. So again, let me write the augmented matrix, then give you 30 seconds for you to try it. Okay, go ahead. So I'll start slowly. That's how I take care of the first column. So that's going to give me 1, 2, 1, 1. Minus 3 this plus this, 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 minus 2 this plus this, minus 2 this plus this, minus 2 this plus this, and minus 2 this plus this. And this is the reason why I'm doing this question, is that once I finish working with the first column, I turn my attention to the second column, and what do you realize? I can't have a leading one over here. It's impossible, and I can't even switch these two rows, because let's say this number was 8, then I can switch the two rows and get the leading one there. But because this number is 0, that means I can't have a leading one here. So I can't have a leading one in column 2. So I'm skipping column 2, and I'm going right away to column 3. And now my leading one will be here, because that's the next row for leading ones. We have a leading one in this row. The next to get a leading one would be here. That's the next leading one. Remember, leading one means it's the first non-zero entry in a row that's not all of 0. So the first entry that's not 0 is here. So I take row 2 divided by -4 into row 2, which gives me 1, 2, 1, 1, 0, 0, 1, 3, 0, 0, -2, -6. Now I got the leading one where I need it to be. I need zeros above and below it. So minus row 2 added to row 1 into row 1, and 2 row 2 plus row 3 into row 3. And this gives 0, 0, 1, 3, 0, 0, 0, 0. Now minus this plus this is this. So X got its leading one, very happy. Y did not get a leading one. Y gets a parameter. I don't know why I'm writing in blue, but X got a leading one, Y did not get a leading one, and Z got a leading one. So Y gets the parameter, and now we solve line by line. This line tells me that Z is equal to 3. This line tells me that X is equal to -2, and then I move the 2 over -2t. And this is the solution for any t. And if we want to write it in vector form, then it's x, y, z is equal to vector for constants, vector for coefficients of t's, -2, -2t, 0, 1t, and 3, 0t. I just wanted to make sure that you see it in every possible angle, and that's basically systems of linear equations. Any questions, any issues with this before we move on? How are you sure? Andrea, that's a good question. Let's say you wanted to get a leading one in that column, right? The leading one cannot be here because you already have a leading one here. There's a one already there. So the options is to have it here or to have it here. Is there any way you can transform these zeros to make them a leading one? You can switch these two rows, but then you'd still have a zero over here. There's no way that I can change that zero into a one. You see what I'm saying? So that way we cannot have a leading one in that column. Okay. So let us switch topics. I'm going to a new page because it's totally worth it to start afresh. Linear transformations. REF, Liam, yes, but RREF is unique. So REF may not be unique. As I said, some teachers allow for constants rather than ones. Remember, I told you this yesterday. Sometimes they allow the leading one to be a different number, but definitely RREF is unique. This is why in most exam questions, we ask us to go to RREF, because that way we'll have the same answer always. RREF is absolutely unique. There's no two versions of it. Okay. So what are linear transformations? Look, the idea is very straightforward. This is like when you learned about functions. A linear transformation, that's like a function. It's a function of vectors. Basically, this is a function, but then of vectors. In the sense that you say, okay, t of a vector u gives me a vector v. Literally like functions, but functions of vectors. So that would be the name of the function of the transformation. That would be the input, the vector u, and that would be the output, which is the vector v. Transformations, linear transformations, are basically functions of vectors. So let me give you an example of a transformation. Let's say you have t is a transformation where you give it a vector in R3, it gives you a vector in R2. We're allowed to change dimensions. And for example, the transformation of the vector x, y, z is equal to x minus z, y plus x, or x plus y, whatever. I just made something up. So for example, somebody tells you, what's the transformation of the vector 1, 1, 1? You're literally applying the rule here. So it's x minus z, 1 minus 1, 0, x plus y is 2. Transformation of 1, 1, 1 is 2. So what would be the transformation of, let's say, 0, 0, 1, 0, 0? That would be the vector 1, 1. And so on. We're not going to give several examples. So this is what it means to be a transformation. Let me give you another example. I will tell you why I'm doing two examples. So let's say we also go from R3 to R2, or not. Let's go from R2 to R3 now. And the transformation of a vector xy, let's define it to be 2x, x plus y, and 1. Something. So what would be the transformation of the vector 1, 1, 1? That would be 2, 2, 1. And so on, and so on. Great. This is what a transformation means. Now, what does it mean when we say a linear transformation? Okay, so linear implies what? Look, there's two ways you can see this. And I'm going to explain, obviously, both of them to you. One way to look at this is option number one, is to say that t is linear, so t is linear, if it satisfies two very important properties. The transformation of vector v1 plus vector v2 is the transformation of vector v1 plus the transformation of vector v2. Obviously, if it's minus also it works. And the transformation of alpha times v1 is alpha times the transformation of v1. Remember when we talked about subspaces and we said it's closed under addition and closed under scalar multiplication? I mean, remember this. So it's if you have an addition, the sum, the transformation of a sum is the sum of the transformation. So, and the transformation of a scalar multiplication is a scalar multiplication by the transformation. I like to think of this as what happens on the inside happens on the outside. Like if you're adding the vectors, then you add their transformations. And if you're multiplying a vector by a scalar, then you multiply the transformation by the scalar. Or we think of linear transformation. T is linear, and if T is a matrix transformation. What does it mean it's a matrix transformation? It means the effect of T can be summarized, can be given by a matrix multiplication. I'll show you. So, for example here, can I describe this? I'm going to practice this with you in just a second, but I'm going to give you these two examples. For example, is this linear? This is option one. Is it linear? Yes, you have the option of doing this, and I am going to do this with you. But so you can see it right away. Is this linear? Well, look, can I describe the effect of this as a matrix transformation? And yes, you can. Just remember this hashtag. Think augmented matrix, right? Hashtag augmented. So what would be the augmented matrix of this? It would be 1x, 0y, minus 1z, 1x, 1y, 0z, times the vector x, y, z. You understand what I mean by hashtag augmented? It's like as if you're writing the augmented matrix of the system. And see this matrix A, this matrix, we call it represents T. This matrix induces T. So we can say A, the technical words are A induces T, or A represents T, or I don't know what other words you want to use. So T of the vector V is basically A times the vector V. The effect of T can be described by a matrix multiplication. Okay, let's show you this. Was this linear? So this one, what about this one? Make them bullet points. Is this one linear? Can you describe this using an augmented matrix? So you can say 2x, 0y. You can take 1x and 1y, and then what do you do with the last row? Well, you cannot express this as a matrix. So therefore, T is not linear. Now, I'm going to show you how to show that it's not linear using the other method also. Right? So this T is not linear. Okay, now using the properties. So using the properties, let's show that one is linear and one is not linear, but we have to agree on something. And this is a very important note. We talked about this when we did subspaces. We talked about this when we mentioned subspaces. If you want to prove that something is true, you must do it in general. If you want to prove that something is true, you have to do it in general. If you want to prove that something is false, all you need is a counterexample. Right? We talked about these when we were solving for subspace, when we were checking if they were subspaces. So if I want to prove that something is true in general, I have to use the general proof. If I want to show that something is false, then all that I need is a counter example, and that's it. So let's have fun. Let's show that this is not linear using the properties. So is this linear? Well, let's show that this is not linear. So you can decide whatever property you want. This fails them both. So let's say you take the transformation of a vector x1, y1 is the vector 2x1, x1 plus y1 is 1. The transformation of a vector x2, y2 is the vector 2x2, x2 plus y2, and 1. So what is it that we want to know? We want to check if the transformation of the vector x1, y1 plus the vector x2, y2, if it is equal to the transformation of vector x1, y1 plus the transformation of vector x2, y2. We want to check if that holds. Marth, have you done it this way? I'm using the properties because I'm worried that they haven't given you this. Like, did you take that theorem that if a matrix, if a linear transformation must be a matrix transformation and a matrix transformation must be a linear transformation? Sometimes last term I had a note here that some students said they didn't see this. So that's why I you actually haven't seen this. So Z is saying that they actually have not seen this. So this is why I prefer if you choose like the method number 2. So using the properties is how it's solved on past tests. So your teachers solve it this way. Though it is a theorem, like I didn't invent it, it is a theorem that a transformation is linear if it's a matrix transformation, and any matrix transformation is a linear transformation. The proof isn't actually that hard to do, but we're not going to do it. So this is why I'm focusing on using the properties, because they seem to want you to use those. I don't know what to tell you, Sydney, right? So choose one way and do it. Right, this is definitely a theorem that if T is linear, then it's a matrix transformation, and if it's a matrix transformation, then it's linear. And some people are saying that you have done it, so you're fine. Again, choose the thing is, I'm not the one that's marking the test, right? So maybe I don't know, fire up an email. Not all of you at once fire up the same email, but like, you know, maybe one person would just ask the question in class or something like, can we say this? Is it enough to say that it's a matrix transformation to show that it's linear? They might just say yes, and you're done. But I'm showing you this both ways just to be safe. So this one is the transformation of the vector x1 plus x2, y1 plus y2. This is not a linear transformation, math. So this one that I'm doing right now is not linear. So those are the same things, Evan. The matrix transformation is a transformation written as a matrix product. Those are the same thing. And math, once again, this is nonlinear. So the transformation of this vector, look, what does the transformation does? It takes 2 times x plus y, and 1. So this gives me 2 times x, so 2 times x1 plus x2, x plus y, so x1 plus x2 plus y1 plus y2, and 1. While what is this? This is this plus this, which gives you 2x1 plus 2x2, x1 plus y1 plus x2 plus y2, and 2. And you see that those are not the same, because here you get 1 and here you get 2. Therefore, T is not linear. Okay, let me show you one that is linear. Let's do the one from 2021. No, we don't want systems of linear equations. We want linear maps. Here you go. Oh, find the standard matrix of L. Very nice. So they're not really asking you to show that it's linear. They're just asking you to find the matrix transformation. This is great. So fantastic. Okay, well, let me do one small proof of it being linear. So I'm gonna do a small proof of showing that it's linear, just in case. So let's take the transformation from R2 to R2. Let's say where the transformation of xy is equal to x plus y 2x, let's say. And now we're going to show that T is linear. Show that T is linear using the properties. Of course, what is the matrix that induces T on the On the side, what's the matrix that represents T? It's 1, 1, 2, 0. Right? Once again, hashtag augmented. So you write the augmented matrix. So this is the matrix that represents T. Because we are able to find this matrix, that means T is linear, no problem. Let me do a small proof to show you that it's linear. We're going to do it once anyway. So you see it, and then you may use it, you may not. Depends on what the question is. So first, we want to check that the transformation as the sum of the transformations. So the transformation of x1, y1, you know what? I'd like to do a, b, c, d. So the transformation of ab is a plus b to a. The transformation of CD is C plus D to C. Now we want to check if the transformation of AB plus CD is equal to the transformation of AB plus the transformation of CD. Well, on this side, this is the transformation of the vector A plus C, B plus D, which gives us what? The transformation adds the components, then takes 2 times the first component. So x plus y, so A plus C plus B plus D, and then 2 times x, so 2 times A plus C. While here, the transformation of AB is this, plus the transformation of CD is this, and when you add them, you will get A plus B plus C plus D, and 2A plus 2C, and those are equal. So that's great. Next, we want to check if the multiplying by a scalar thing works. So the transformation of, you can stay with AB or you can go with XY. I'll do AB. The transformation of AB is A plus B to A. So we want to check if the transformation of alpha times AB gives us alpha, the transformation of AB. So on this side, this is the transformation of alpha A, alpha B. So what does that give me? It's x plus y, so alpha A plus alpha B, and 2x, so 2 alpha A. On this side, it's alpha times the transformation of AB, which gives me alpha A plus alpha B and 2 alpha A, and we can see that those are equal, therefore T is linear. Again, this is the absolute longest way of doing it. Usually when we're asked if T is linear, we could just say it's a matrix transformation, thus it's linear. Again, I invite you to double check that you could use this, but it's definitely a theorem. Like I did, it's not a method that I invented, it's a well-known method. All right, now what are we gonna do with those linear transformation? Now we're just gonna build some knowledge, and once I build some knowledge, we're gonna go and we're gonna practice problems left, right, and center. So a very important note about linear transformations, and this is very, very important. If T is linear, then the transformation of the zero vector must give me the zero vector. Please note that it's not the other way around. Some people think that, like, if the transformation of 0 is 0, then it's linear. That's not true. I'm even going to write it as a note. So, but, I'm not use but, if T of 0 is equal to 0, then it could be linear. or it could be not linear. We don't know. So if it's linear, then the transformation of 0 is 0. But how is this useful to us? How is this useful to us? How can this be used in a useful way? To be used in a useful way, this is how you use it. You say that if the transformation of 0 isn't 0, then guaranteed t is not linear. I think you call this the contrapositive. So the transformation of 0 isn't 0, then automatically t is not linear. By the way, you have it right here. See here, let's write this as a green note. What's the transformation of the vector 0, 0 here? What's the transformation of the vector 0, 0 here? It would be the vector 0, 0, 1. See, this is not the 0 vector, therefore automatically t is not linear. You see, that's another layer, that's another indication that your transformation isn't linear. Okay, let's continue. Again, this is the stage where we're just building up knowledge, like I'm explaining concepts and things you need to use. Then once we have enough of these, we'll just go and we will practice. So what is the composition of linear transformation? So what's the idea of composition of transformation? So let's say L1 or T1, whatever you like to call it, is a transformation that takes us from a vector space U to a vector space V, and U1 is linear. Let's take L2, which is a transformation that takes us from V, vector space V, to vector space W, and this is linear. See, now we can define the transformation L2 of L1. Remember this in functions? L2 composed with L1. And what does this mean? It means you start with L1, you go to L2. So it means this is defined as L2 of L1 of a vector U. So let's just write it. So that means you start in U, you go to V, L1 takes a vector in U, gives you L of U equals to V, then L2 takes V, which is the L2, this is, I should write their indexes. L2 takes L1 of U, which is V, and it gives you a vector W and W. Of course, these must be the same, or this is not a good transformation, right? The image of one transformation should be the domain of the other one. So where one ends, the other one starts. And there is a theorem that this is also linear. So when you do composition of linear transformation, you get a transformation that is linear. Okay, let me give you an example. Sometimes too much abstract is annoying. So let's take you have L1, which is a transformation that takes me from R2 to whatever you want. So let's say R3. And for example, the transformation of XY, we can write them not as vectors, we can write them like a sleeping down vector. So you want to come up with a linear transformation? And then L2 takes us from R3 to whatever you want. Let's say R3 and stays in R3. So what is the transformation of X, Y, Z? So let's say L1 is, it just switches them, Y and then X, and then does X plus 2Y. And then here, what do you want L2 to do? It doubles X, it minuses Y, and here it adds all of them. So whatever, we're just giving an example. So this is linear. By the way, if you want to write the matrix A1 of this, the matrix A1, the first row is Y, so 0, 1, 0, 1. The second row is X, so 1X, and the last one is X is equal to 1, 1, 2. So this is the matrix that induces L1. What's the matrix that induces L2? The first row is 2X, so 2, 0, 0, 0, minus 1, 0, and 1, 1, 1. Notice the sizes. Notice the sizes. A1 has size 3 by 2. A2 has size 3 by 3. The size of the matrix is always image cross domain. So I'll write this on the side. So if you have a transformation T that takes you from Rn to Rm, image is like where you then, and T is linear, I'll say that again. Then the matrix A will have size M by N, M by N. So this is the domain. This is where your transformation starts. This is where your, like, this is your range, let's say. Right, domain and range. Range or image, I'm gonna tell you what the image is in just a second. So how do we write L2 of L1 of a vector V? Right, and V has to be in R2 because L1 starts in R2 and it goes to R3. So this is L2 of L1, and let's say the vector is XY. L1 of XY is this, so this is the transformation of the vector YX, X plus 2Y. And what does L2 do? L2 takes 2 times the first component, so 2 times Y. It does minus the second component, so minus X, and it takes the sum of all 3 components, so Y plus X plus X plus 2Y. So this gives you the vector 2X minus X, 2X plus 3Y. And you can clearly see that this is a linear transformation. By the way, the matrix here, let's call it B. This is 0, 2, minus 1, 0, 2, 3. And if you want an extra theorem, I don't think you need this theorem, but in case you want to learn something extra, this is A2 times A1. Because you say L2, L1, so A2 is the matrix of L2, A1 is the matrix of L1, so this would be the matrix B that gives you L1, L2. If you need composition, this is what composition is. I'm going to pause for a second and you'll let me know if you have questions. I don't see any questions. So now let's talk about some serious stuff, right? You're still with me. What is the kernel of a linear transformation? Now we're beginning with the last phase of collecting information. Once I tell you what the kernel is, what the image is, we'll take one theorem and then we'll just move on to solve problems. So let's say we have a transformation L or T from a vector V, from a vector space V to a vector space W. What is the kernel of L? Please, please, please pay attention, because if you learn this once, then you just know it forever. The kernel is a set of vectors. right? The kernel is a set of some vectors v in V. Okay, I'd like to do it now so I don't go back to it later. Which step are you talking about, Sydney? How do I go from here to here? So look, what does L2 do? L2, when you take L2 of a vector, it does twice the first component. So L2 of this vector, you do twice the first component, so 2y. Remember here, the first component is y. Then L2 does minus the second component. So the second component is y. So here you do minus the second component. The second component here is x, so it does minus x. And then it adds all three components. So you add this, which gives you this. Right? So that's how I got L2 of that vector. No problem. Thank you for asking. So now we're focused on kernel. So kernel of a transformation is all the vectors in V such that when you do the transformation of those vector, you get the zero vector. Of course, in W, say 0 in W. But whatever, you just get the zero vector in W. So it's the set of all the vectors in V such that the transformation of those vectors gives you the zero vector. Who can give me an obvious vector in the kernel? Who can give me a very obvious vector in the kernel? The zero vector, right? So since the transformation of the zero vector is the zero vector, then the zero vector belongs to the kernel of L. Of course, I'm talking about like the zero vector in V. But you know, when you put something inside the transformation, we know that it's coming from V to W, and the answer must be a vector in W. So we don't always put the zero on the W when it's awesome. So the kernel is the set of vectors such that the transformation of those vectors, it's all the vectors in V, such that the transformation of those vectors gives us zero. And it's a big theorem that the kernel of L, the kernel of a transformation, is a subspace, SS, subspace of V. Yeah, we're saying it's linear. I mean, technically, it doesn't have to be linear for this definition, but you only learn linear transformation. The kernel can be defined for any transformation, Evan, right? But in your case, you only work with linear, so you can write linear, or you could just not write linear, it doesn't matter. Do you understand what I'm saying? Like, the kernel is the kernel, whatever the transformation is, but you only work with linear transformation. Now, what is the image of a linear transformation? Okay, so the image, so let's say we have a linear transformation from a vector space V to a vector space W. The image of L is the image. So now we're talking about in W. So it's all the vectors W in W. So it's all the vectors in W such that there is a V in V with a V is equal to W. So it's all the vectors in W such that you get them by such that there's a vector V such that, sorry, this is no AV, such that L of V is equal to W. So it's the range. You know how the range of a function is? So it's the range is all the values Y such that there's an X with f of X equals to Y. So it's the values in the range where f of x would give you that value. Same thing here. The image of a linear transformation is all the vectors that are in W in the range, where we can get those vectors by doing L of a vector V gives me W. And there is another theorem that says that the image of L is a SS subspace of W. I think we even showed that those are subspaces. We showed that those are subspaces in midterm 1. I think I've done this, maybe not. So please, let's say this differently. If I tell you that V, vector V, belongs to the kernel of a linear transformation, then what can you tell me about V? If I tell you that, hey, I was walking today and I found a vector V in kernel of L, then what can you tell me about V? That means L of V is equal to 0. Right? A vector is in the kernel if L of that vector gives me 0. So if I told you that W is a vector in the image of L, then what can you tell me about W? Then what is your conclusion? Then your conclusion must be that there is V in V such that the transformation of V is W. So there is a vector somewhere such that the transformation of that vector would give me W. W is a vector that I can get by the transformation of a vector V in V. Now, something that is super important, this is very important. We know that the image is a subspace of W. If you want to say it like that, sure, Evan. And kernel is a subspace of V. So kernel is a subspace of V, and image is a subspace of W. Now, super major important theorem, the dimension of the kernel. Now I'm going to ask you what is the dimension, and you're going to answer me because you know this from yesterday. And if you don't, I'm going to remind you. Plus the dimension of the image space is the same thing as the dimension of V. So if we have a linear transformation that takes me from V to W, then the dimension of the kernel plus the dimension of the image gives me the dimension of V. This is a very, very important theorem. Now, let's do a small review because sometimes we forget. So just a very, very quick 2-minute review. What is the meaning of dimension of a vector space? What's the dimension of a vector space? You remember this from yesterday. It's the number of vectors in a basis. So the number of vectors in a basis. We can think of it as the maximum number of linearly independent vectors in the space, in the vector space. So this, the maximum number of linearly independent vectors. You cannot have, more than those independent vectors, and this would be the least number of vectors to span the vector space, right? You cannot span the vector space with less than the dimension. Remember, we said this yesterday. I'm gonna take 2 more minutes to review this. So yesterday we said that when we talk about a basis is a set that's a generating set, and it's a set that is linearly independent, right? So it's a generating set and it's linearly independent. We talked about the basic lemma, I think it's called. We said that if we have vectors v1 up to vk, I think we used k yesterday. So if we had v1 up to vk that are a generating set for v, and the dimension of v is n, then what can I say about k and n? And we said that if we have v1 up to vk are linearly independent in v, and the dimension of v is n, then what can I say about k is n? And this one is silly, but we'll do it either way. If v1 up to vk is a basis for v, and the dimension of v is n, that what can I say about k and n? This, by the way, all of this was done yesterday. I'm just doing a review. So if you're looking at this and thinking, wow, he's going super fast, I am, because I'm just doing a reminder. The video for yesterday's session, if you weren't there, will be posted shortly if it's not posted already. So you'll be able to watch this in details, but in yesterday's video. So who can answer me this? If we have this a generating set for v, then what's the link between k and the dimension of v? If it's a generating set, that means k is bigger than or equal to n. So you need at least n vectors to span the space. So if the dimension of v is n and you have a generating set, then you need at least n vectors. Now, even if you have n or more, it's not guaranteed. You have to check. But at least if you have less than n, it can never be a generating set. If v1 up to vk is linearly independent, we know that the maximum number of linearly independent vectors is the dimension. That means definitely k is less than or equal to n. Because we know that they're linearly independent, so they cannot exceed n. N is the maximum number of linear independent vectors. And if we know that v1 up to vk is a basis, that means k must be equal to n. And all of this from the definition of the dimension right here. Do we get this, guys? So what I'm trying to say is that the dimension of the kernel, so the maximum number of linearly independent vectors in the kernel, plus the dimension of the image space is always equal to the dimension of v, the vector space where the transformation starts. Do I make sense? Okay, so next topic at hand is, now we just go to practice. So now we're gonna find, so finding a basis for the image space of a transformation and the kernel of a transformation. Actually, let's start by finding a basis for the kernel. Then we discuss a small review of a matrix. Oh, I haven't proved this to you. I will prove it to you later when we practice this, Evan. Because this will be the rank of the matrix A. This will be n minus the rank of the matrix A, and that's n. I haven't proved that to you. I will prove it to you later when we actually find them. So thank you for saying. If you don't understand why, the proof, I mean, we're not proving rigorously, but I will tell you why just later. Regardless, whether you understand why or not, this is definitely needs to be memorized. Right, Evan is right. I didn't prove this yet, and I will tell you a little bit later why this is when we find a basis for the image and the basis for the kernel, and it will be not so difficult. You'll see. But whether we know why or we don't know why, we absolutely have to remember this. The dimension of the kernel plus the dimension of the image is always the dimension of the vector space V that we've started with. Okay, I'm gonna pause for a second. Do you understand all of this? At least this part. And do you understand how to apply this? Not how to prove this, but how to apply this. So if you have the dimension of the kernel, then you have the dimension of the image. And if you have the dimension of the image, you have the dimension of the kernel. Definitely there's a lot of practice coming. So we've just finished sort of collecting the information. So let's see. Let's start with our first example. We are going to get a break in 4 minutes. I just want to get through this one example, Mark, and then we will take a break. We're going to take one break today. Instead of taking 2 breaks of 15, we're going to take 1 break of 20. So we'll save 10 minutes, and really there's no need to go and come back. We'll just do it once and we'll rest. So let's say we have a transformation L of, let's say L is a transformation that takes me from R3 to R2. And let's say that the transformation of a vector L, X, Y, Z is whatever, X plus Y, Y plus Z. We want a basis, so find a basis for the kernel of L. I promise you this is not as difficult as it looks like. Linear algebra has this annoying thing where we use a lot of terms, like find a basis for the kernel of L. This is just so like theoretical. Basically, we're saying find a basis for the kernel of L. In the, like on the street, you're just asking to solve L, X, Y, Z equals to 0, 0. Right, see, look how funny linear algebra is. If I tell you this is the linear transformation, solve L, X, Y, Z equals to 0, 0, I'm pretty sure like, a lot proportion of you won't panic. Like, yeah, okay, so I have Lx, is equal to this. So I have X plus Y, Y plus Z equals to 0, 0. Then I solve, no problem. I say to you, find a basis for the kernel of L, and people like freak out. Oh my God, basis, kernel, I hate linear algebra. They're just exactly the same thing. Right, so what's the basis for the kernel of L? So X, Y, Z belongs to the kernel of L if the transformation of X, Y, Z is 0, 0. And that's what we are solving. We're just solving Lx, Y, Z equals to 0. So Lx, Y, Z is X plus Y, Y plus Z. You're setting this equal to 0, 0. So you literally have like a system. X plus Y equals to 0. Y plus Z equals to 0. We can go and write an augmented matrix. 1, 1, 0, 0, 0, 1, 1, 0. So this is not an RREF yet. It takes one step. So minus row 2 plus row 1 into row 1. So 1, 0, minus 1, 0, 0, 1, 1, 0. X got its leading 1, Y got its leading 1, Z didn't get a leading 1, no problem. So Z gets a parameter. So I solve this, Y equals to minus T, and X is equal to just T. Therefore, I'm solving for X, Y, Z. So I discovered that X, Y, Z is just T times 1 minus 1, 1. Well, what do you know? This becomes the generating set and the basis for kernel of L. So that means the vector 1 minus 1, 1, this is in fact a generating set for the kernel of L. Because what are we saying? We're saying that X, Y, Z is in the kernel if X, Y, Z has this form, right? X, Y, Z belongs to the kernel. So X, Y, Z has this form, which means X, Y, Z is just the span of 1 minus 1, 1. Therefore, 1 minus 1, 1 is a generating set for kernel of L. It is linearly independent because it's clearly just one vector. Therefore, a basis for kernel of L is just that, which means the dimension of the kernel of L is equal to 1. Absolutely, Peter. Very quickly, X got a leading 1, Y got a leading 1, Z did not get a leading 1, so Z gets the parameter. This line tells me X minus Z is equal to 0. So when you move the Z over, it becomes X is equal to Z, but then Z is T, so X is T. And this line says Y plus Z is equal to 0, so Y equals to minus Z, so Y is minus T. So that's how we do that. Right? Final question to you before we take a break. What is the dimension of the image of L? Come on, make me happy. What's the dimension of the image of L? I remind you that L starts from R3 and it goes to R2. Julia, I'm going to give you another chance. Good job, Julia. So the dimension is 3 minus 1, which is equal to 2. So this is V. L goes from V to W. So the dimension of V is equal to 3. And we know by the famous theorem that the dimension of the curl of L plus the dimension of the image of L is supposed to be 3. So if the dimension of the kernel is 1, the dimension is the dimension of the image is 2. And of course, after the break, I'm going to tell you how we find the A basis for the image and all of that jazz. Are we okay up till now? So break time. Right now it is 2:19. Let us be back at 2:39. I want to ask you, please, 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 everyone, to fill in the evaluations. The evaluations are very dear to me. The link should be posted in the chat. Usually people who think I'm crap will run to the evaluations and they'll do them, and that's their right. I just hope that, maybe also the people who think I'm, we're going to do another one. We're going to do the same problem, but same type, but with different numbers. So I'm hoping that, good or bad, you will all take the time to just tell me how this is going. And yeah, it just literally takes a minute. So I'm going to give you that minute. So let's be back at 2:40. It's a nice round number, please. And then we're gonna go one shot from 2:40 to 4 p.m. Basically doing transformations and more examples. And definitely, this is not the last time we find the basis of a kernel. Definitely, we're gonna do more of this. All right. Thank you very, very much, and see you in 20 minutes. Hey everyone. So let's see. As promised, another example of the same thing. This one was, I gave that to you. So here we go, linear maps. Here we go, that's a good enough example. So this is 2021. So there's this one. This will teach us some more things. Nope. Well, this is basically finding the kernel of L as part T, but let's do it. So let L be the linear transformation from R3 to R3, given to us by this. Find the standard matrix of L. So to find the standard matrix and not make a mistake, I'm going to write it one on top of the other. So X plus Y, Y plus Z, and then X plus Z. So the standard matrix of L is A is equal to X, Y, no Z, Y and Z, and then X, no Y and Z. Very simple. Part B. Determine whether 0, 1, minus 1 belongs to the kernel of L. So how do I know if a vector belongs to the kernel? So basically, I find the transformation of 0, minus 1, 1. So the transformation of 0, 1, minus 1 is X plus Y, 1. So I don't care what's left. So this is not in the kernel. So X plus Y, Y plus Z, X plus Z. This is not equal to 0, 0, 0. Therefore, 0, 1, minus 1 does not belong to the kernel. Remember, vectors belong to the kernel if the transformation of the vectors are 0. Are we okay on this? You're not saying anything, so I'm assuming we're okay. Does this vector belong to the image of L? So how do I solve that? Does this vector belong to the image? So 1, 1, 2 belongs to the image of L if there is a vector x, y, z such that the transformation of x, y, z gives me 1, 1, 2. So literally, I am solving L, x, y, z equals to 1, 1, 2. And L, x, y, z is right here. So that means I am solving x plus y equals to 1. Y plus z is equal to 1. And x plus z is equal to 2. By the way, we can think about it this way, or we can solve it, or we can say a times x, y, z is equal to 1, 1, 2. But that's fine. We could do it this way. So we can write the augmented matrix. Look at the augmented matrix. 1, 1, 0, 1. 0, 1, 1, 1, 1, 0, 1, 2. You see? So this is matrix A, and this is the vector 1, 1, 2. This is what I was saying before. Right? Right? So I'm not gonna I'm not gonna do this all in detail. So I'm gonna say if I reduce this, I'm gonna do this very fast. So 1, 1, 0, 1 minus this plus this minus this plus this minus this plus this. and then this is 0, 1, 1, 1, then minus this plus this, minus this plus this, minus this plus this, and this plus this, and then this plus this, and then this plus this. So yes, there is. So this is 1, 1. So minus this plus this, minus this plus this, and this plus this, and this plus this. So when you solve it, of course, do it slowly. We get the answer is x is equal to 1, y is equal to 0, and z is equal to 1. So the transformation of the vector 1, 0, 1 gives me the vector 1, 1, 2. Therefore, definitely 1, 1, 2 belongs to the image of L. So I just did the reduction here very fast, but do we get the theory of this? Excellent. Let's see part D, the kernel of L. So the kernel of L, which means now we're gonna say that x, y, z belong to the kernel of L. That is equivalent to saying the transformation of x, y, z is equal to 0, 0, 0. Now, the nice thing about this is you're gonna start with the matrix, like you're gonna do the same thing as this. So it's basically this, but instead of 1, 1, 2, you're gonna do 0, 0, 0. To find the kernel. So basically you're gonna get the same augmented matrix, but instead of 1, 1, 1, you're gonna get 0, 1, 1, 2, you're gonna get 1, 1, 0. So basically you're gonna get the same final result, but instead of 1, 1, you're gonna get 1, 1, 0. Which tells you that x is equal to 0, y is equal to 0, and z is equal to 0. So x, y, z belongs to the kernel, means x, y, z is just 0, 0, 0. So that means the kernel of L only contains the 0 vector. There's no other vector in the kernel. The dimension of the kernel is 0. So there's nothing in the kernel other than the vector 0, 0, 0. Now, for part E, they say decide with proof if L is inject. Yeah, all kernels contain the 0 vector, which means the kernel here only just contains just the 0 vector. Right, Alex? All the kernels contain the 0 vector anyway, like the transformation of 0 gives us 0. So this means we call the kernel here, the kernel is trivial, if you want. Like it's basically the 0 vector and nothing else. You understand what I'm saying? So the kernel is just 0. By the way, well, there is nothing in the kernel except the 0 vector. So the dimension is 0. If you had one parameter here, like if you had a t in there, you would get a, let's say, dimension of 1. But since it just contains the 0 vector, so the dimension of the kernel is 0. Right, Evan? There's nothing in the kernel except the obvious 0 vector. Trivial means it's just the 0 vector and nothing else. 0 vector and nothing else. Like it's the only obvious vector, right? We all know that the 0 vector belongs to the kernel, right? Because the transformation of 0 is 0. Everybody knows that the transformation of 0 is 0, so 0 belongs to the kernel. So the kernel is trivial. The kernel is nothing but the 0 vector. What do you mean with the previous theorem? You solved for the dimension of the image with the previous theorem, right? The dimension of the image of L is equal to what? Here. So the dimension of the kernel is 0, and this starts from R3 to R3, then the dimension of the image of L is 3. Therefore, by the way, image of L is equal to R3. Why is that? Because image of L is a subspace of R3, right? Because L goes from R3 to R3, and the image is a subspace of the range. And since the dimension of the image of L is 3, which is the same thing as the dimension of R3, therefore the image of L is equal to R3. Right, and how do I get 3? It's 3 minus the dimension of the kernel, 3 minus 0. Makes sense? Now, how do we know that L is injective? Injective means 1-to-1, meaning if the if x1 is not, if v1 is not equal to v2, this is equivalent to the transformation of v1 is not equal to the transformation of v2, or we can just make it in terms of equal. Right, so it's 1-to-1. No v1 gets 2 images, and no one image comes from 2v1. If the inputs are different, then the outputs are different. You can do it in terms of different or equal. And because there's a theorem that you definitely learn in your notes, that L is injective, is equivalent to the kernel of L being just 0, or the dimension of the kernel of L being 0. So yes, L is injective because the dimension of the kernel is 0. It means if you have 2 different vectors, then they will go to 2 different images. That's what it means for L to be injective. And if L is injective, then the kernel is just 0. And if the kernel is just 0, then L is injective. This is a two-way kind of theorem. Okay, let me show you one more example of finding the basis for the kernel. 2019 had a nice one. Basis for image L, I have to show you later. Okay, so let's just pick this, and we'll just do a basis for the kernel. So this is from 2019. I'm going to do all of it, but in just a second. I have one more thing to explain to you, then I will be able to solve the whole thing. I want you to find me a basis for kernel L. Again, I'm going to solve the entire 2019 question in a second, but first, how would you get me a basis for kernel of L? Okay, take a moment to set this up. We're definitely not going to do the whole row reduction. So I'm opening Wolfram. So we could do it really quickly. So X, Y, Z, W belongs to the kernel of L. That means that the transformation of X, Y, Z, W is 0, 0, 0. So X plus 2Z plus W should be 0. Y plus 4Z plus 3W should be 0. And 2X minus Y minus W should be 0. So we get the matrix 1, 0, 2, 1, 1, 0, 1, 4, 3, and 2 minus 1, 0, minus 1 with 0, 0, 0. I want to stress the fact, guys, that this is the matrix A. Because what's the matrix that describes the transformation? It's X, Y, Z, W, X, Y, Z, W, and X, Y, Z, W. You see how this is just A? So you're solving, because why? Why is that? Because Lx, yz equals to 0, 0, meaning A times X, Y, Z, W equals to 0, 0, 0, 0, which basically gets you this. Right? So the transformation is described by a matrix multiplication. This is why we get this, not by complete chance. Because if you go from this to this, you get this. And if you go from this to this, you get back this. Like you always end up with A with 0 next to it. In some questions, they give you RREFA. So in some questions, you are given RREFA. So they save you the trouble of doing it really fast. Now here we're not, so I'm gonna do it really quick. 1, 0, 2, 1, 0. Or we can just simply check the solutions. Do I even have the solutions close by? Let me check. Because there's 3 equations, Johnny. Look, it goes from R3, from R4 to R3. So you have 3 components. 1, 2, 3 components. Right? So the first component is 0, the second component is 0, and the third component is 0. Right, I don't have it. 2019. I'll just solve it myself. I don't have it somewhere close. So this is 0, 1, 4, 3, 0. Then minus 2 this plus this, 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 0. Then this plus this, this plus this, this plus this. Then minus this plus this, then minus 2 this plus this, then this divided by half, and here we are. So dot, 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 of course, to get to here. So W is equal to T. No, not W. Yeah, actually W is equal to T. Because W does not get a parameter. How does that become 0 again? Sorry, let me double check my work. Minus 2 this plus this, minus 2 this plus this, minus 2 this plus this, and minus 2 this plus this, then this plus this plus this. Yes, I was right. So W is equal to T. W doesn't get the leading one. So X, Y, Z, W. We know that Z is equal to 0 from this line. We know that Y is equal to minus 3T from this line. And we know that X is minus T from the first line. So X, Y, Z, W is T times minus 1 minus 3, 0, 1. So basically, this is a basis for kernel of L. So a basis for a kernel of L is minus 1 minus 3, 0, 1, which means the dimension of the kernel of L is 1. And if we get asked the dimension of the image space of L, is equal to, so this goes from R4 to R3, so 4 minus 1, which is equal to 3, because that's what this line tells me, Andrea. Right, Z does not depend on W, it's just Z equals to 0. Do you see that? No problem. So by the way, the dimension of L is 3. So you know that the image of L is a subspace of R3 and its dimension is 3. Therefore, the image of L is R3. Absolutely, Evan. The 4 is from the R4, yes, Alex. 4, that's the dimension of R to the power 4. Does that make sense? Okay. Now I want to add just a little bit of like a small reminder of what I told you earlier about matrix transformations being linear transformations. So what is a matrix transformation? This will only take a second. We've done most of this. A matrix transformation, which is an equivalent idea for linear transformation. So a linear transformation is a matrix transformation, and a matrix transformation is a linear transformation. It's any transformation from V to W where L of V, the effect of L, is described by A times V. Right, so the effect of the transformation is described by a matrix, and we did say this is all done before. I'm just reminding you that if L goes from Rm to R, let's say from Rn to Rm, then A, and this is linear now, we need it because we need it to be a matrix transformation, then A would have size M by N, always range by domain, M by N. Well, how many vectors does it have in the basis? Because it has one vector in the basis. Right, the dimension is the number of vectors in the basis, maximum number of linearly independent vectors. Don't forget, where is it? Don't forget those that we did yesterday, right? Those are very, very, very important. Right? So, now we just The only thing that's left to say, that is the image of a linear transformation is basically the same thing as the image of its matrix A. And that is the span of the columns of A. So when we say the image of a linear transformation, which is what I told you before, this has the same definition as before. Now we're going to give it an extra definition. So let me stress that so you don't think we changed the definition. The image of L is all the vectors W in W such that there is V in V with L times V equals to A times V is equal to W. So this has not changed. This is the same as before. This is still a subspace of W. None of that has changed. We're just now saying that the image of L is the same thing as the image of the matrix that describes L, which is the span of the columns of A. Now, how do we find a basis for the columns of A? So a basis of image A is what? Please pay attention. Those are the columns of A that ended up with a leading one. Let's specifically say with a leading one in RREFA. So it's the columns of A that ended up with 1. So the columns of A that ended up with a 1 in RREFA. So you look for the RREFA, you find out which columns got a 1, and those are the columns that are that will be the basis of the image space of L. Okay, why is that? Why is that? So just a small explanation, although you don't really need it. The columns of A are a generating set for the image of A, right? Because the image of A is the span of the columns. So the columns are the generating set. So the columns of A that are linearly independent meaning they ended up with a leading one, form a basis of A. So this is just a quick explanation. So you find the columns of A that ended up with a leading one in RREFA, and those form the basis of the image of A. So as promised, I'm going to go back and do that problem from 2019. So this is the problem from 2019. We did already the part about finding the kernel. RREF, I think you missed yesterday, Agu. We talked a lot about this yesterday. Reduced row echelon form. RREF, this is the reduced row echelon form. This is the reduced matrix of A. So we did explain this yesterday. So please review yesterday's notes. My notes today will be posted as soon as we finish, and the video of yesterday should be made available soon. So please review those. We definitely covered that yesterday. But in short, it's the matrix that is reduced. So Find the standard matrix of L. So A is equal to, A, of course, we're going to be 3 by 4. 3 by 4. Oh, the video from yesterday is already available. Wow, Course Cram is on fire. So here you go, you could just watch it. So this would be 3 rows, 4 columns, 1, 0, 2, 1. We did this already. 0, 1, 4, 3, and then 2, minus 1, 2, minus 1, 0, minus 1. So the image of L is the same thing as the image of A. So we're gonna go and get the reduced row echelon form of A. I'm not redoing it, I did it already here. This is our REFA. Remember, I reduced it. So what does the theorem tell us? We go to our REF of A. We find out which columns have a leading one. So we find out which columns have a leading one in our REF of A. Then we pick those columns in A. So A basis for image space of A, which is the same thing as the image space of L. You pick the columns in A. So the first column, the second column, and the third column. So you pick the columns in A that ended up with a leading one in our REF of A. So the dimension of the image space of L is 3. Why is it 3? Because it has 3 vectors in the basis. Again, we talked about it yesterday, the number of vectors in the basis, that's the dimension. And that's it, everything else we've done in this problem. Right? Okay, I'm going to show you an example from 2020. You said you didn't have 2020. And I've been solving all the questions from it, so you can have 2020. So this is done, this is done, this is done. We did this, we did this. I'm going to do this later. So the last one is number 5. So this is from 2020. This is a very nice problem from 2020, and we're going to go over it together. There's one small notion left for me to cover for you. Doesn't that, I'm sorry, say that again. Doesn't have that basis have all the x's together? I'm really not sure what you mean by all the x's together. Maybe you want to elaborate a little bit more. So this is question B. While I copy this, this is question C. And this is question D. An excellent question. So let's do that. So we have a linear map. They told us that it's linear. Evan, I don't understand the question. Maybe you want to clarify it. So we have this linear map. Each of the vectors in the basis we just found was all x's in one, all y's in the other. No. We found, Evan, the column 1, column 2, and column 3 of A. Why is it column 1, column 2, column 3? Because column 1 had a leading 1, column 2 had a leading 1, and column 3 had a leading 1. So you pick the columns with leading ones and you write them down from A. It just happens that it's column 1, column 2, column 3. It could have been column 1, column 4, or column 1, column 2. Like it could have been any number of those columns. So we are told that this is a linear map for functions where the transformation of f is f double prime minus f. So, for example, they're giving you examples of how to do this. So what's the transformation of e to the 5x? The transformation of e to the 5x is e to the 5x double prime minus e to the 5x. Yes? So if you do this twice, this is 25 e to the 5x minus e to the 5x, which is 24 e to the 5x. Magnificent. What's the transformation of e to the 5x plus e to the 4x? Now we're told that it's linear. So this is the transformation of e to the 5x plus the transformation of 4e to the x. You can do it this way, or you can do e to the 5x plus 4e to the x double prime minus e to the 5x plus 4e to the x. You'll get the same answer either way. So if we do it this way, so, this or this. So the transformation of e to the 5x, we have it. It's 24 e to the 5x plus the transformation of 4e to the x is 4e to the x double prime minus 4e to the x, and that's 0, right? Because no matter how many times you derive e to the x, it stays e to the x. So we get so 24 e to the 5x. Notice what we just got here. This is the transformation. This is the transformation of e to the 4x. Now for some theory. Is L injective? See, I'm doing this to make sure that you understand what injective means. Injective means if F1 is not equal to F2, then it's equivalent to the transformation of F1 is not equal to the transformation of F2. It's injective, it's 1-to-1. To remember this, I tell my students, it's dating when nobody cheats, right? So, if F1 and F2 are different, then the boyfriend or girlfriend of F1 are different. So, like, F1 not equal to F2, so image of F1 not equal to image of F2. Like there's no two Fs go to the same image and no two images come from the same F. So is it injective? Exactly, this is not injective because the transformation of e to the 5x is 24 e to the 5x, and the transformation of e to the 5x plus 4ex is 24 e to the 5x. So two items, two inputs got the same output. So no, because the transformation of e to the 5x turned out to be the same as the transformation of e to the 5x plus 4e to the n. Those two are different, so their images should be different, and they're not. Okay, so is the dimension of the kernel bigger than 0? Yes or no? See, this is the theorem that I told you about. It's Evan, it's not e to the 5x that goes to 0, the other one. The answer is yes, it must be 0 because the dimension of the kernel equals to 0 is equivalent to L being injected. So because L is not injective, therefore, so yes, because the dimension is 0 means L is injective and L is not injected. Sorry. Sorry, I'm just going to tell them. Okay, so that means the dimension of the kernel is bigger than or equal to 0. Now, furthermore, as Evan is saying, give me an element in the kernel other than 0. I'm saying the kernel is 0. Mark, I'm not saying the kernel is 0. I'm saying if the dimension of the kernel is 0, then L is injective. The kernel being 0 is equivalent to L being injective. And because L is not injective, it means the dimension of the kernel must be bigger than 0. Do you understand what I'm trying to say? Now, furthermore, to push this even further, who can give me an element in the kernel? So what's an element? What's a function? Give a function in the kernel of L other than 0. And the answer is 4e to the x, right? We just saw it right here. This is why I highlighted it. The transformation of e to the 4x gave us 0. Basically, any number times e to the ax belongs to the kernel of L. Right? Because no matter how many times you derive it, the transformation of L e to the ax is a e to the x double prime minus a e to the ax, and that just gives you 0. Exactly. If something was injective, then one thing goes to 0, and that's 0. Do you get what I'm saying? Like if the function is injective, if L is injective, and then one item can just go to 0. Like L of one thing only can be 0. And because L is linear, then that thing must be 0. So no other thing is allowed to go to 0. You can also see it that way. Right? And ladies and gentlemen, so that was 2020. That was fun. Finally, there is one last note about transformations, and that completes the whole thing. So one more thing to learn, and then we would have completed everything. An important note. If L is a linear transformation, so if L is a linear transformation, if A represents L, very, 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 very important, then the columns of A are the effect, are the image, or the effect are the image of L of the standard basis. Very important. Let me explain this further to you. So let's say L goes from R3 to R2. And A represents L. So L of a vector V is A times V. So A represents L. First thing, what's the size of A? What's the size of A? And L is linear, of course. We said linear. So L would be 2 by 3. So A would be 2 rows, 3 columns. So there's one column, and then that's it. right? So this is 2 by 3. What I'm trying to say is that this column 1 of A is the transformation on the vector 1, 0, 0. Standard basis, guys. So 1, 0, 0, 0, 1, 0, and 0, 1, 0. Column 2 of A is the transformation on 0, 1, 0. And column 3 of A is the transformation on 0, 0, 1. Columns. I'm sorry, do we do rows by columns or columns by rows? I'm not really following. Like the column is the transfer. Do you want me to write it as like the transformation of 0 or 1, 0, 0 like this? Like the column. The size of the matrix is always this by this. Yeah, it's rows by columns. Rows by columns. So this is 2 by 3. 2 by 3, that means it has 2 rows and 3 columns. Right, so let me give you an example of how we would be able to use this. Let's go to, I don't know, 2021 had a nice one. Here we go. Well, this one, 2019 is just as good. This is it, by the way. This is everything we need to learn. So after this, maybe I'll look if there's any interesting questions, but that's it. It's been a good ride. So let's see. Suppose L is a transformation from R2 to R3, and it's a linear transformation. We know that L of 2, 3 is equal to 3, 0, 2. L of 3, 4 is 2, 1, 1. So part A, I want to write 1, 0 and 0, 1 as linear combinations of 2, 3, and 3, 4. So this is very midterm 1-ish. So I want to write 1, 0 as A times 2, 3 plus B times 3, 4. And I want to write 0, 1 as C times 2, 3 plus D times 3, 4. So we have 2A plus 3B is 1. 3A plus 4B is 0. You solve this however way you want. And then 2C plus 3D is 0. And 3C plus 4D is 1. Sorry, guys, just 1 second. So, we solve this however way we want. I don't know, let's say, so if I multiply, I don't know how we want to solve this. So L3, 4. So I don't know, let's just do this matrix wise. So 2, 3, 1, 3, 4, 0. So I am gonna use the software. So report. So this gives me 1, 0, minus 4. So when you solve this, you're going to get A is equal to minus 4, B equals to minus 3, B equals to 3. And if we have the other one, 2, 3, 0, 3, 4, 1, you definitely know how to RRF it. And that's going to give you here, when you solve, C is equal to 3, and D is equal to minus. So how can we use this? So basically, I'm going to write it down. 1, 0 is minus 4 times 2, 3, plus 3 times 3, 4. And 0, 1 is equal to 3 times 2, 3, plus, actually, minus 2 times 3, 4. Always, now they're asking us to find the standard matrix of L. So we want to find the matrix of L. We want to find what A is equal to 2. And by the way, A is 3 by 2. Please remember, A is 3 rows, 2 columns. So there's basically 2 columns. Column 1 of A is the effect of L on 1, 0. Actually on, 1, 0. And column 2 of A is the effect of L on 0, 1. In R2, the standard basis is 1, 0, 0, 1. So column 1 is the effect on 1, 0, and column 2 is the effect on 0, 1. So how do I know what L1, 0 is? See, this is why they asked us to do that. So the transformation of 1, 0 is minus 4, the transformation of 2, 3, plus 3, the transformation of 3, 4. And the transformation of 0, 1 is 3, the transformation of 2, 3, minus 2, the transformation of 3, 4. That's why they asked us to do this in the first place. So the transformation of 2, 3 is 3, 0, 2. The transformation of 3, 4 is 2, 1, 1. So this is minus 12, 0, minus 8, plus 6, 3, 3. So this is minus 6, 3, minus 5. So minus 6, 3, minus 5. And the transformation of 0, 1 is 3 times 3, 0, 2, minus 2 times 2, 1, 1. So 9 minus 4 is 5. Minus 2, 4. So you get 5 minus 2 and 4. Ta-da! So the columns of A are the effect of the transformation on the standard basis. And then they asked us to find L45. So you can find L45 in 1 million ways. So you can say L45 is basically A times the vector 4, 5. So you can take the matrix minus 6, 3, minus 5, 5, minus 2, 4, and multiply it by 4, 5. But maybe you haven't done matrix multiplication yet. So if you haven't, you can do this in a different way. You can say that 4, 5 is 4 times 1, 0, plus 5 times 0, 1. So you can express 4, 5 in the standard basis. So that means the transformation of 4, 5 is 4 times the transformation of 1, 0, plus 5 the transformation of 0, 1. So the transformation of 1, 0 is minus 3, 6, minus 5. The transformation of 0, 1 is 5 minus 2, 4. Well, if you haven't. And that would be minus 24 plus 25 is 1. 12 minus 10 is 2. Minus 20 plus 20 is 0. Or this, right? You could have done this. This is a matrix that's 3 rows, 2 columns. This is 2 rows, 1 column. So the result is this. So this times this minus 24 plus 25 is 1. 12 minus 10 is 2. And then 0. So you can see that you get the same answer. I think we should do one more like this. So let's do that. Let's go to this. 2021. We did that. Oh, this one's nice. Prove or disprove that L is a linear matrix. I'll tell you in a bit. Let's do this. So this is definitely something more fun. I'll say it in a second. If you haven't done it in class, Evan, then you probably need to do it in the other way. But what you do is you take this, you multiply it by this, and then this you multiply by this as a dot product, and this multiply by this as a dot product. Right? Or what you do is you can say 4 times the column minus 6, 3 minus 5 plus 5 times the column 5 minus 2, 5. So that's one other way of doing it. Either you do this dot this, then this dot this, then this dot this, and you get the 3 entries. Or you can take this times the first column plus this times the second column. That's matrix multiplication. Okay, so let's end on this, which is definitely a different, more difficult type of problem. Recall the weird vector space that apparently they've seen this in class that year. So under the following, so we have addition is defined that way, and scalar multiplication is defined that way. There is a linear transformation from a function, from all functions to W2, and it's defined by the transformation of a function f is e to the power f at 0 and e to the power f of 5. Prove or disprove that L is a linear transformation. So that's something. So prove or disprove that L is a linear transformation. That's going to involve us using the properties, right? So that's going to involve using the properties. So we're going to check that the transformation of f plus g is the same as the transformation of f plus the transformation of g, and the transformation of a scalar is going to be that. So let me just double check what year was that in. That can be from 2019. I think that was, where did I get that from? Oh, 2022. Very nice. So they went crazy in 2022. That was, I think students got scared of it. So let's see, how do we do this? Well, we're going to prove that the transformation of the sum is the same thing as the, see, that's not even 2022 that I have. I don't know where that question is from. I have no idea where that question is from. I'm saying 2022, but I don't know where that question is from. So let's assume it's some test somewhere. But the 2022 I have doesn't have this. I'm looking at the, oh, sorry. I apologize. I'm looking at the wrong midterm. Sorry. Yeah, it is 2022. Sorry, I was looking at a different midterm. I apologize. Okay, so let's see. Let's do what is the linear transformation of a function f plus a function of g? Is it equal to the transformation of the function of f plus the transformation of the function of g? So the transformation of f plus g, that would be, wait, so these are functions here, very good. So this would be the transformation of f plus g is e to the f plus g at 0, e to the f plus g at 5, which is equal to f plus g at 0. So this is e to the f0 plus g0, e to the f5 plus g5. And we know that we can write this as e to the f0 times e to the g0. And this is e to the f5 times e to the g5. Because when you add the exponent, that's like a multiplication. What's the transformation of f plus the transformation of g? Remember, plus is like a weird plus, right? Because here we are in W2. So the transformation of f is e to the f0, e to the f5, weird plus, e to the g0, e to the g5. Now, how does weird plus function? We multiply them. So this is going to be e to the f0, e to the g0, e to the f5, e to the g5. Well, what do you know? Those are equal. G is another function. So let f and g be functions in C infinity of R. Like instead of calling them f1 and f2, I'm calling one f and one g. Right? I don't want to use f1 and f2. There's way too many indices in this problem. So I picked up two functions in here, and I'm checking that L of f plus g is the same thing as L of f plus f of g. Now that's passed. Let's check the other one. So I want to verify that L alpha times f is the same thing as alpha times L of f. Remember that this alpha here it's a weird multiplication, because that's, here you're still in C alpha R, so here you're still in functions. Here you are in W2. In W2, the scalar multiplication is redefined as this. So what is L of alpha f? This is e to the alpha f at 0, e to the alpha f at 5. What's alpha times L of f? So alpha times L of f is e to the f0, e to the f5. And what is the alpha? You take the x and you raise it to the power alpha. So this is e to the f0 to the alpha, e to the f5 to the alpha. And when you have double powers, that's e to the alpha f0, you multiply them, e to the alpha f5, and what do you know? Those are equal. So L is linear. And that is one big, nice problem. while we're at this, wasn't there a second part to this? Transfer. Oh, it was in linear independence. So let's do the second part of this. This was a weird enough problem, so let's continue with weird enough. So let's look at this. If V and W are vector spaces, L is a linear map. Let V1, V2, V3 be such that they are linearly independent. Show that, or prove or disprove that their images are also linearly. So we know that they are dependent. We want to show that their image is also dependent. So there's a very, very easy way of showing this. We can say that V1, V2, V3 is dependent. So V1 is equal to sum A V2 plus sum B V3 for sum A and B not equal to 0. Right? And you guys, I'm posting the notes in like under 10 minutes. So you're going to be able to copy that. So if these vectors are linearly dependent, then one of them is just a linear combination of the others. So LV1, because this is linear, is A times LV2 plus B times LV3, right? Because it's a linear combination. It's a linear map. So you just the transformation of the sum is the sum of the transformation. Then you pull the constant out. So clearly, we've just shown that LV1, LV2, and LV3 is dependent. Look, one of them depends on the others. Now, if I may add one more problem before we go. So let's do it if it's independent. So let's say V1, V2, and V3 are independent. Can you show that L of V1, L of V2, and L of V3 is independent? Actually, it goes either way. So this works both ways. So if those are independent, then those are independent in either way. So what does it mean? So now I'm just showing this one. But I'm saying it does work the other way around. So V1, V2, V3 are independent. This means that AV1 plus BV2 plus CV3 equals to 0 has only, this is the very important, only the solution A equals 0, B equals to 0, and C equals to 0. So let's check those. This one, yeah, I mean, this is a perfectly good answer. So now let's take alpha LV1 plus beta LV2. Let's just say A1 V1. So A1 LV1 plus A2 LV2 plus A3 LV3 equals to 0. And they are independent if A1 equals to 0, A2 equals to 0, and A3 equals to 0 is the only solution, right? So let's check. So this would be L of, by the way, AV1 plus AA1V1 plus A2V2 plus A3V3 is equal to 0. Now, because L is linear, that means A1V1 plus A2V2 plus A3V3 is 0 because L is linear, right? The only thing that goes to 0 is 0. Therefore, A1 is equal to 0, A2 is equal to 0, and A3 equals to 0 is the only solution. Because we know that V1, V2, and V3 are independent. Therefore, the set of images is also independent. I'm gonna attach the midterm by topic at the end of these. And that's it, ladies and gentlemen. That's APSC 174, midterm 2. So I'm gonna post here the midterm by topic after this. So after this, thank you everyone. If you have any questions for me, don't hesitate to email me. I wish you the best of luck, and I think most likely we'll see each other at some point for the finals. So thank you very, very much. Have a great rest of your weekend at office. Thank you very much. And I'm posting the notes right now. I'm logging off. Bye, guys.
Record.